So now that we've got some of the basics down, let's make this a little bit more interesting. And let's look at example 3. We want to solve y double prime minus 2y prime minus 3y is equal to 4x minus 5 plus 6x times e to the 2x. So there's a couple of things going on here that's different than the last couple of problems. We have a linear function here, and then that last term, we have a linear function times an exponential. So let's figure out how we can set up this particular problem. So the first step is always to solve the associated homogeneous differential equation. So in this case, our associated homogeneous differential equation is y double prime minus 2y prime minus 3y is equal to 0. The auxiliary equation would be m squared minus 2m minus 3 is equal to 0. That factors into m minus 3 times m plus 1. So we get 3 and negative 1 as roots for that auxiliary equation. So our complementary solution is c1 e to the 3x plus c2 e to the negative x. Okay, now I do want you to notice there is not a repeat here with this and what's going on there. And remember, we use this piece to figure out that educated guess for our setup to solve for that particular solution. So let's make that educated guess. So remember, our particular piece looked like this. So this is a linear piece. We could write that as ax plus b. And this is linear times exponential. So we could write as cx plus d times e to the 2x. So if we were to multiply everything out, we would have that. Now the reason I could use just e to the 2x here instead of a coefficient times e to the 2x is because when I distribute there, I'm still going to have that coefficient in front of those e terms. So there's what our particular solution is going to look like. So this guy's pretty massive, right? So it's going to make sense for us to kind of split that into a couple of pieces where we consider the linear piece and then the piece that has the exponentials. So I'm going to separate this. And then we can use that superposition principle to put those pieces back together. So I'm going to let that first piece, I'm going to split up basically this particular solution into YP1 and YP2. So if I use that linear piece as YP1, then we need to take first derivative and second derivative. First derivative is a, second derivative is 0. So we're going to make our substitution into the differential equation. So our differential equation was y double prime, which is 0, minus 2y prime, which is a, minus 3 times y, which is ax plus b. And that has to be equal to the linear piece of 4x minus 5. So let's create our system. Comparing coefficients of x, we have minus 3a on the left and 4 on the right. So we already know a is going to be negative 4/3. And then we have, comparing constants, we have a minus 2a on the left, minus 3b. And then on the right, that's going to be equal to a negative 5. We can substitute in what we know. And then solve for b. So when I solved this, I ended up with b as 23/9. So then our particular solution, yp1, is equal to negative 4/3 x plus 23/9. Those coefficients go in for those two variables, those numbers. So now let's look at that part that contained the exponentials, which we are calling yp2, which is cx e to the 2x plus d e to the 2x. So we're going to take derivatives. And we're going to use product rule. So we're going to have first function times derivative of the second plus second function times derivative of the first. And then take the derivative of the second term. I'm going to clean it up. And then find yp2 double prime. Once again, product rule. First one, derivative of the second, plus second, derivative of the first. Take the derivative of the second term and the derivative of the last term. Clean it up. So now we're going to take all of this and substitute it into the differential equation. So our differential equation is y double prime minus 2 times y prime minus 3 times y equals, going back up to the original, 6x e to the 2x. So let's start comparing coefficients on the left and on the right. And I'm going to be careful when I do this. I'm going to go ahead and distribute before I start doing that. So we have x e to the 2x terms. If we look at what's going on the left and on the right, I have a 4c here, a minus 4c here. Those terms actually cancel. I have a minus 3c here, and that's got to be equal to 6. So that tells me that 3c minus 3c has to equal 6, which means c has to be equal to a negative 2. And then I have e to the 2x terms. So we have a 4c here, minus 2c. I could have combined those. Minus 4d. Let's try that again. Erase my underlines. We have 4c plus 4d minus 2c minus 4d minus 3d is equal to 0 because we don't have an e to the x or e to the 2x on the right hand side. So just combining some like terms here, 4c minus 2c is 2c, 4d minus 3d is a minus 3d. Once again, we could have combined everything above. So we have 2c minus 3d is equal to 0. Let's make our substitution. We already know c is negative 2. So if we were to substitute that in, that's going to tell us what d is. And it looks like it's going to be negative 4/3. So that means our YP2, remember this is going in for those coefficients C and D, would be negative 2x e to the 2x minus 4/3 e to the 2x. So our particular solution, remember we split this up to look at the linear piece and look at the exponential piece separately. We could have done it together in one massive equation by making substitutions for, going back up here, let me write out something. So we could have done this in one massive equation. We could have said that's just yp all together, and then we could have done yp prime and yp double prime. This would be pretty lengthy, and those would go in for those guys. So we would have had a really massive equation to solve. Breaking it up into smaller pieces just made it a little bit more manageable, but you totally could have done this in terms of one massive equation. So when we split it up, we looked at the linear and the exponential piece separately. So now if we put that particular piece together, it's going to be yp1 plus yp2. We said yp1 was negative 4/3 x plus 23 over 9. And yp2 was minus 2x e to the 2x minus 4/3 e to the 2x. So there's our particular solution. So what if we want that general solution? Well, the general solution is the complementary plus the particular solution. So we use that superposition principle here where we found YP1 and YP2 and we added them together. We're using it again here when we found that general solution by adding the complementary and the particular solutions together. So our final solution is the complementary plus that particular. So there's our final solution for this problem. So now that we feel really comfortable with that, let's look at example 4. In example 4, we're going to see that there's a little bit of a glitch in our assumption here, and we're going to have to make a tweak to fix that glitch. So they're giving us second order differential equation and they're asking us to find that particular solution. So we would start by thinking, well, what does our educated guess look like? Well, an educated guess would be ae to the x. So if we wanted to make a substitution into that differential equation to solve for a, we would find the first derivative and the second derivative, and then we would substitute in. So second derivative minus 5 times the first derivative plus 4 times y, and that's going to be equal to 8e to the x. But look at what happens when we try to create that system. If we were to combine like terms on the left, we end up with 0, which is 0ae to the x is equal to 8e to the x. Well, this is telling us essentially 0 is equal to 8, but that's a contradiction. 0 is not equal to 8 typically. Okay, so that means there's something off somewhere. So let's go back and look at what that associated homogeneous solution would look like. And that's why that piece is so important when you're solving these types of problems to really look at before you start. So the associated homogeneous differential equation would be y double prime minus 5y prime plus 4y is equal to 0. The auxiliary equation would be m squared minus 5m plus 4 is equal to 0. That factors into m minus 4 times m minus 1. So we get 2 roots, 4 and 1. So we know the complementary solution is c1 e to the 4x plus c2 e to the x. So there's where our problem is. We made a bad assumption in the beginning. We assumed that we would have something in the form of y equals a e to the x, but that would be a repeat from the complementary solution. In other words, these two are not linearly independent, and our solutions have to be linearly independent. That's why we ended up with this contradiction when we made that faulty educated guess. So you have to look at that associated homogeneous differential equation first, figure out what those solutions are going to be, make sure you don't have any repeats. If you have a repeat of something like we do here, then you have to mend what your educated guess is going to look like. And we can use the same theory that we had talked about in previous sections, where when we had a repeated term, like in this case we would have a repeated e to the x, then we would use the particular solution of a times e to the x. And where we tweak that e to the x, we made this assumption earlier, but we need to tweak that by multiplying it by x. Now let's see what happens if we apply this. So our yp prime, this would be product rule. First derivative of the second plus second derivative of the first. Second derivative, first derivative of the second, plus second. Let me try that again. First derivative of the second plus second derivative of the first. And then the derivative of the second term is just a e to the x. Combine some like terms here. And now we can make some substitutions again into the differential equation. Our differential equation was y double prime minus 5y minus 5y prime, let me correct that, plus 4y. And that's going to be equal to 8e to the x. Let's do some fancy math. Distribute. I'm going to combine like terms before I start. Looking at the x e to the x terms, it looks like they all cancel. Looking at just the e to the x terms, we have 2a minus 5a would be a minus 3a e to the x has to be equal to 8e to the x. So that means that minus 3a has to be equal to 8, which means a has to be negative 8/3. So it turns out our particular solution is negative 8/3 x e to the x. So then general solution is complementary plus particular. So we have c1 e to the 4x plus c2 e to the x minus 8/3 x e to the x. So if we just wanted the particular solution, there it is. We've already found the complementary. It's really necessary to find the complementary so you have that linear independence between the pieces. These two are now linearly independent because that second e to the x term is multiplied by an x, which forces the independence there. So let's practice that a little bit and let's look at example 5. We're just looking at what that form is going to look like for the particular solution. So for part A, we have y double prime minus 8y prime plus 25y is equal to 5x cubed e to the negative x minus 7e to the negative x. So to me, it looks like we could factor out an e to the negative x, and that leaves us with 5x cubed minus 7. So we have an exponential times a cubic. So a particular solution would be an exponential times a cubic also. So e to the negative x times ax cubed plus bx squared plus cx plus d. Okay, but we have to double check, since this has an exponential in it, we really need to double check to make sure we don't have any duplication, and that's where that complementary solution really needs to be looked at. So we got to check for duplication in that complementary solution just to make sure that we have the form that we need. Otherwise, when we work it out, we will get some kind of contradiction, and we've done a lot of work really for no good there. So if we look at that associated homogeneous differential equation, we have y double prime minus 8y prime plus 25y is equal to 0. Auxiliary equation would be m squared minus 8m plus 25 is equal to 0. This guy does not factor, so we're going to use that quadratic formula. So it's negative b plus or minus square root b squared minus 4 times a times c all over 2a. So 64 minus 100 is 36. It's negative, so we're going to have imaginary roots. So we already know there's not going to be any duplication there. We've got 4 plus and minus 3i. So the complementary solutions is going to be c1 e to the 4 plus 3i x plus c2 e to the 4 minus 3i x. And using Euler's, we could factor out an e to the 4x, leaving us with c1 e to the 3ix plus c2 e to the negative 3ix so we would have c1 times cosine of 3x plus I sine of 3x plus c2 times cosine of minus 3x plus I sine of minus 3x. Using even odd properties of cosine and sine, we can condense this to now a c3 times cosine of 3x plus c4 times the sine of 3x. Where C3 and C4 could be complex. So notice there's no duplication between this and what our educated guess was up here, which means this is where we need to start to solve this problem. Now, we're not going to go through and solve it, but that's where you would start. We're just asking for the form in this problem, but you always have to check for duplication. So let's do that next one. Same thing, find the form. So if we think about what it could be, we have a linear term times a cosine term. So the linear term could be expressed as ax plus b. Cosine could be expressed in terms of sines and cosines. So we would have c sine of x plus d cosine of x. So if we were to multiply this out, we would have AC x sine of x plus AD x cosine of x plus BC sine of x plus BD cosine of x. Now we've got quite a few variables in here. I'm going to simplify this just a little bit. A constant times a constant is just another constant. So I'm going to call it, I could call it A1, B1, C1, D1, or I could just call it EFGH. Now, this one does have sines and cosines. We need to look at that complementary solution. So if we look at that associated homogeneous differential equation, it would be y double prime plus 4 is equal to 0. And we know this guy will have imaginary solutions. M is going to be plus or minus 2i. So we see the complementary is going to be c1e to the 2ix plus c2e to the negative 2ix. So if we apply Euler's formula here, and I'm just going to go ahead and do that, we would end up with c3 times the cosine of 2x plus c4 times the sine of 2x. Skipping a few steps in there does simplify that, where C3 and C4 could be complex. We're looking for duplication. Is there any duplication between this and what our form looks like here? And no, we see that the angles are different. In the particular solution, we're looking at sine of x, cosine of x, sine of x, cosine of x. But in the complementary, we're looking at cosine and sine of 2x. So those angles are different. So we don't have any duplication there. Which means our particular solution looks good, and then we could go through that process of finding that associated homogeneous differential equation. Finding the particular solutions and then substituting everything in, finding those first and second derivatives. We're just asking for the particular solution. So that's what a particular solution, that's what the form would look like. That's the most important thing. And once you get the form, everything else is really just a little calculus and algebra thrown in.